and then you can see the slide, right? Slides are visible. Just gives a, yeah, okay, good. So what I'm going to do is try to finish the discussion on these set of slides. So we started talking about continuous random variables, and um, the point was these are random variables whose distributions are determined by this probability mass function. Sorry, probability density function. And the probability density function is something that you integrate to give you the probability of an event. So if you want to obtain the probability that random variables between A and B, or in this interval, basically A and B, um, you integrate the function over that interval. That function is called the probability density function. Um, and the interpretation is that um, the probability that x lies in, let's say, a small interval, a up to a plus epsilon, roughly is equal to f of a times the length of that interval, which is epsilon. So if the interval is small, the function is roughly constant. So if I'm looking at this small interval, the function is roughly constant here, fx of a. And so what I would get is fx of a times the length of the interval gives me the probability. So um, that kind of tells you that then if you divide, for example, by this epsilon, basically this is the limit would be the f of x at a. So it's really a density. So the probability divided by length, by unit length. So a PDF is really probability per unit length at a particular point. And so this can vary. Here, for example, this little interval has more probability. So it's more likely that you find x in this interval than, for example, in this interval. And the exact ratio is kind of determined by the PDF. So another way of saying this is really this fx dx is really the probability. This is roughly approximately the probability that x belongs to x and x plus dx. Okay, so this is like easy to remember. And so when you integrate it over x, this gives you like a macroscopic probability. So f of x itself is again not probability, but once you multiply by a length, unit of length, that gives you something of type probability. And so this has to integrate to 1 because over the entire real line, because the probability that x takes a value in the real line should be 1. And it should also be non-negative. You can see it from here because the value is really a probability divided by length on a small scale. It has to be non-negative. So these are the two properties. Given these two properties, then a function would be PDF. There is no other constraint other than being integrable. Um, and yeah, so these are the things that we discussed. Any question about this? So the idea is kind of important. Um, and it's different than the way that we just did like work with discrete random variables. Discrete random. So one consequence of this is that the probability that you take any like single value, like the probability that x takes value x equal to a, is going to be 0. So if you look at something like the PDF, sorry, PMF, it doesn't make sense because the probability it takes any particular value is going to be 0. This might be not intuitively clear, but if you think about it, if you have a random variable, continuous random variable, the chance that you get this particular value is 0. But there is a chance that you get it like in an interval around that value. And that gives you the, it's given by this. Anyways, so another way of So this PDF characterizes the distribution because allows me to compute the probabilities of these events. And once I have the probabilities of lying in intervals, then I can compute the probabilities of more complicated sets. Another way to characterize the distribution of a continuous random variable is via the CDF. So this CDF is also um, enough because it tells you the probabilities of like um, half infinite intervals. And so this is the probability that x belongs to negative infinity and x, right? And so that would be similar exactly to the discrete case. And this makes sense in the continuous case because this is like a macroscopic interval. And if you remember the formula, basically in order to compute the probability based on the PDF, we need to integrate the density from infinity to x. Here t is a dummy variable, so it can be anything. But the key is that I'm going to integrate it up to x from negative infinity. And so this is the relation between the CDF of a continuous random variable and its PDF. And if you remember the um, like fundamental theorem of calculus, um, fundamental um, theorem, something like that. It tells you what is the derivative of this integral. So if you take the derivative of this, it's a function defined as an integral. The derivative would be exactly the integrand evaluated at x. And so the derivative of the CDF would be the PDF. So the relation is the CDF is the integral of the PDF is the derivative. Um, and if you draw the CDF of a continuous random variable, um, it doesn't have jumps. So it gradually, as you integrate, it gradually rises from 0 at infinity to 1 at sorry, at negative infinity is going to be going to 0. At positive infinity it goes to 1. But in the limit, this happens, and it continuously varies. So it's going to be smooth. And then the derivative would be like the slope would determine the PDF. So the PDF starts to go down here. As you can see, the slope dies down. And this corresponds to the fact that the PDF cannot, like, has to go down. It goes down as you go to positive infinity and negative infinity. The mass cannot, like, accumulate at infinity. Um, Another general view is like it's just the distribution of mass. So the PDF tells you how the mass is distributed. Basically, the area under the PDF is the probability. So it's just think of it as like just the pile of mass. That's the easiest way to think about it. The areas that has more mass are more probable. The areas that have less mass, they're less probable. So it doesn't have to be necessarily unimodal. It could be the PDF could be something like this, like go up and down. The PDF can do anything really, subject to those constraints that f is non-negative and f is uh, integrates to 1. Integral of f is 1. But the CDF really is gonna be monotone, okay, monotonic. Plotting it wouldn't be easy here, but it's not gonna have it's going to be monotonic, but it's just the slope would change. So maybe, so the areas where it rises the slope, so it starts, slope would be high, then maybe low, and then high, and then low, and then something like this. Okay. So areas corresponding to the peak would cause this to rise faster. Areas where it's a valley, it kind of flattens a little bit. It's not exactly flat. It's going to be always increasing because this is not 0. In cases where there is kind of potentially you could have like a PDF that has something here and then 0 here and then jumps again. So in this part, because there's no mass, the derivative is 0. So here would be corresponding to this. If you look at the CDF would be flat here. So it goes up, and as it goes down here, it's going to be flat, and then it goes back up and starts to die. So is this going to be here? Exactly flat. So flatness of the CDF would correspond to the PDF being kind of zero exactly. Like it has to be zero in an interval, not at a point it doesn't matter. Okay, this comparing this to the CDF of a discrete random variable, which is just basically jumps. So it's like flat jumps, and so on. And the jumps tells you the value of the PDF, PMF. Any questions about this? So and then we did a quick example, I believe. So this is like an example where f of x is x over 2 from 0 to 2. And the reason why it's x over 2 is because over 0 to 2 is because it has to integrate to 1. The 1/2 is doing that. So this is a valid PDF. And for example, we used this formula to calculate the CDF, and the CDF would be basically the red curve here that I showed. Okay, and then we talked about the expectation and the variance. So the idea is very similar to the discrete case, except that in the discrete case we did define the expectation uh, as the summation over all possible values of x that the random variable can take, x times the basically the PMF, px of x, which is really x times the probability that x takes the value x. So this does not gonna like is not working like does not work in the case of a continuous random variable. As we mentioned, this is going to be zero. But the equivalent version is just the integral. So imagine this is really the meaning of this is the probability that x is around x, little x. Okay, so this has the same form. So x you multiply x by the probability that the random variable takes almost that value, like in a small interval, and then you sum. The sum turns into an integral. Okay, so that's uh, the equivalent version. So you integrate x times the PDF. So this is the PDF, probability density function. And that gives you the expectation. Once you have the expectation, you can define the variance. The variance is usually defined as the expectation of x minus the expectation of x squared. This is what we defined or used last time. And this is also equal to the other expression that we have here is equal to star. Okay, so the expectation of x squared minus the expectation of x squared. So the variance remains the same once you define the expectation. The variance is defined in terms of the expectation, and it has the same meaning. So first, the expectation is right the center of mass for the distribution, and also the limit of the averages of IID random variables in the long run. We'll see that, and the variance has the meaning of like a spread of the distribution. So all the properties that we discussed will carry over the law of the unconscious statistician, the linearity of expectation, this result about the variance that variance of ax plus b is equal to a squared times the variance of x. Um, additivity of the variance over independent sums also carries over. Um, and the fact that it's not additive in general, the variance is not additive, also carries over. Um, so the only thing that potentially you have to worry a little bit about is the independence. And so independence of random variables, like continuous random variables. So let's say x and y are independent. Let's say they're both continuous. The meaning is the same as before. So probability of x belonging to some set A and y belonging to some set B has to factorize x in A times the probability of y in B for any A and B subset R. So we saw that this is kind of equivalent to the joint PMF factorizing in the discrete case. So this definition works everywhere, okay? But for continuous variables, there's an equivalent version which you can write it in terms of this the joint PDF which we'll see. So there's going to be a joint PDF which we'll see later. Um, that takes two arguments, and this is going to factorize as the product of the PDFs. So this is equivalent version in terms of the PDFs, but we need to kind of discuss this um, later. What do we mean by the joint PDF? Um, and it's really something that you integrate over R2 over a set, and it would give you this probability. But just keep in mind that there is an alternative version in terms of the joint PDF factorizing. Um, but even if we don't know that, this is enough. So this fact you already know, and this generalizes. So this works for any pairs of random variables. They're independent if the probability that x takes some value in some set and y takes values in some other set factorizes the product. You know that these you can write as integrals of these, and this is you can write as integral of that, and then kind of in the limit would look like the PDF factorizing. Okay, but let's say if x is independent of y, we have like variance of x plus y is variance of x plus variance of y. This is true in general. It doesn't matter if the random variable is random variables are discrete or continuous. And the reason is kind of we argued it last time. We argued it in the discrete case, but it generalizes to the continuous case. Okay. Questions? Okay. I'll leave calculating the variance of this distribution to you. You can just integrate. Basically, you have to integrate. We can compute x squared, expectation of x squared, which is going to be this times the fx of x dx, which would be integral. This is only non-zero on 0 to 2, so you do this, and then x squared times x over 2 dx, and this should turn out to be 1/2 times 1/3 x to the actually 4 probably, yeah. So they're going to be 4 here. And you do 0 to 2, so you get, so this is 4. So you get 16 over 8, so it'll be 2. So this is 2, and then the expectation we computed last time, so the second moment minus the first moment squared, and then you get the variance. Okay, yeah, there's another like result that is useful for expectation if the random variable is always non-negative. Um, Another way of calculating the expectation, this formula is called the tail formula or sometimes layer cake formula. Instead of doing this, we can do integral of x bigger than or equal to t dt. So this doesn't require you um, to use a PDF, but basically the let's do it like this. For a continuous variable, it doesn't matter if you put bigger than or equal to or bigger. So this is like the complement of the CDF. So if I know the CDF or 1 minus the CDF, I can use this to calculate the expectation. This requires a proof, but I'm going to skip it. If you're interested, we can discuss it in the office hours. So use this to calculate these two. Oh, actually, this one you can't. Or you can, but this one you can calculate using this approach as well. So it's going to be useful. We'll come back to this formula. So this is important. It's like helpful for not. It only holds for non-negative random variables. So the random variables that take like only non-negative values. The example is here. So the PDF only puts mass on 0 to 2. Not on the negative side. So nothing on the negative side. Otherwise, this wouldn't work. Okay, questions? So the rest of this lecture is mostly, or like these set of slides is like just introducing some common continuous random variables. I'm going to go over them rather quickly because it's like not really that difficult to grasp. So you just, if you want to define these continuous random variables, you can give the PDF, for example, or the CDF, and it would just specify the distribution. So the basic one is the uniform distribution on an interval A and B. So this is a random variable has a uniform distribution if the CDF, let's say, sorry, the PDF over the interval is like constant. Over the interval is going to be constant and then zero elsewhere. It's going to be zero here and zero here. And it turns out that it doesn't matter for a continuous variable. For a PDF, the values at a single point do not matter because only we care about the integrals, whether what is it at exact this point, whether it has to be like non-zero or not doesn't matter. So if you define it to be non-zero or zero at any finite set of points, it really doesn't matter. So it could be like this, or you could say, okay, we're gonna define it zero here and then not zero here and then maybe non-zero here. And so these PDFs are equivalent in a sense, which may not be clear at first, but what we really care about is the integral. So this the area under the curve, and if you redefine it as a single point, doesn't change the area. Okay, so it's going to be non-zero generally in this interval, modulo a couple of finite points. For example, the endpoints, we don't care. And because it's constant, it has to integrate. So we know that if I integrate it over a and b, if f of x is constant, let's say some c, when I integrate it over that interval, it has to sum to 1. And so this c comes out. So this would be equal to c times the integral, which is a minus b. So a constant function over an interval integrates to c times the length of that interval. So this c, sorry, this would be b minus a. C has to be, from this it follows that C has to be 1 over B minus A. Okay, so the PDF would be 1 over B minus A on A and B. Let's say here we are defining it to be non-zero at the both endpoints. We can actually define it to be anything. You can like define it to be like any number here. It doesn't have to be zero, doesn't have to be exactly this. You can define it to be anything, doesn't matter really. So for any x, it has this 4. On that interval, it's 1 minus 1 divided by b plus 1 and 0 otherwise. And then you can compute the CDF. The CDF would be linear because once you integrate this, it's going to be 0 here. This is the derivative is constant, so it has to be a line, and then you just are constant again. So the CDF turns out to be this. You can see it's a line, and then the slope is b minus 1 divided by b minus a. So this is the equivalent of the uniform model that we discussed in the discrete case. Remember, in the discrete case, the uniform model would put the same probability on all the outcomes of a finite space. And so the probability of an event would be the cardinality of that set, A divided by the total number of outcomes. This is the equivalent for a continuous distribution. The probability of X belonging to any set would be the length. It turns out would be the length because you're going to integrate something constant. So you get that constant. This is the constant 1 over that. So you get the length of that interval, or like that set, not necessarily doesn't need to be interval, divided by the length of the interval. Okay, so if I look at a particular interval here, the length of this interval divided by AB would give me the probability. Okay, so a very special case is uniform on 0, 1. So if I have X, which is uniform on 0, 1, so that the density would be like 1 on 0 to 1, and then 0 elsewhere. Okay, and then basically the probability that you're in any interval, like that land in an interval, is just the length of that interval divided by 1, so just the length of the interval. And so this is very useful. Then you can compute the mean and the covariance, sorry, the variance. The mean is naturally like the middle of the interval. So you compute it by integrating x times the PDF, which is going to be x 1 over b a dx, a and b, and then you get 1 over b minus a, then 1 half x minus, sorry, x squared, ab, and then you do substitute, you get 1BA times B squared minus A squared, and these simplify, you get B plus A over 2. So it's naturally the middle of the interval. And it's really the center of the distribution. The variance you can compute similarly, and it turns out to be this quantity. Okay. Hopefully you've seen this before. So for a uniform distribution, the mean would be 1/2. The variance would be 1 over 12. So it's good to remember. Any questions? So this uniform distribution has some sort of a universality property. So in universality may not be the good term here. It means a certain thing in modern probability. But what I mean here is you can get any continuous distribution from a uniform distribution. If you manage to create or sample a uniform distribution, then you can create any continuous random variables as a transformation of it. And the reason is this result. So if you have, um, let's say f be a continuous, strictly increasing CDF, so we're like excluding this case where the PDF has zero parts, like things that are have a like a little bit of um, like the flat regions in the CDF. So this PDF you're going to rule out. I'm not going to worry about this. The CDF will be flat, so it's not going to be strictly increasing. So assume you have an increase, like a continuous, strictly increasing CDF. Then if you sample a uniform random variable u, uniform of 0, 1, and then f will have an inverse. This is a proper inverse because it's strictly increasing. It's going to have a unique inverse. So if you set x to be f inverse u, then the CDF of this x would be f. Okay, so conversely, if x has CDF f, if you apply f to x, then f of x has uniform distribution. So these two properties are very useful. The first one is used to calculate or create any random variable. Okay, so if you manage on a computer to generate a uniform 0, 1 distribution, then you can create any um, basically random variable with a strictly increasing CDF. Um, so the proof is very simple. So let's try to prove one. Like the first assertion is uh, so if you look at this inequality, so f minus 1 of u less than or equal to x. Okay, so this is, or another way of saying it. So I want to calculate the probability that x is less than or equal to x. This is the CDF of x evaluated at x. Okay, so this is going to be the same as the probability by definition that f minus 1 of u is less than or equal to x. Okay, this is an event, and this inequality is true if and only if f of u is less than or equal to x. I can apply f to both sides. And because f is increasing, it's not going to change. So it's like what I'm doing is I'm applying f to both sides of this inequality. And because f is increasing, it doesn't change the inequality. Inequality still goes the same direction. And this is u because f and its inverse, when you compose them, you get the identity mapping. Sorry, this would be equivalent to the other way. This is not true. It will be equivalent to, sorry, u is less than or equal to f of x, as you can see here. See here. And so I get the probability that u is less than or equal to f of x, but u is uniform. So for a uniform distribution, so if you have uniform 0, 1, this would simplify. So in the case of uniform 0, 1, f basically of u would be, this would be 1, this would be 0. This would be 0, so you just get x on 0, 1. Okay, so it's going to be just goes as x up to this point, and then it's just going to be flat. Okay, so because f of x is going to be always in 0 to 1, we are in this regime, so we are here. So we're going to evaluate this at some point in 0 to 1. So this is really just going to be another way of doing it is just fu evaluated at f of x, but fu of u is really u for u in 0 to 1. So this just gives me f of x. Okay, this is really all u. So we showed that the CDF of x is really the f of x that we wanted. So this is the key to generate a lot of the continuous random variables. The other way is I'm gonna let you prove it. It's very similar. So if I have x CDF f, if I apply f to x, it's going to be in 0 to 1 because you know that the CDF is between 0 and 1. So it makes sense at least because the uniform is restricted to 0 to 1. And so it turns out to have a distribution uniform 0 to 1. So this proof is an exercise. Proof is very similar as an exercise. Okay, let's see an example. Suppose, yeah, to sample any distribution, draw U uniformly, and then return f minus 1 of u. Basically, one random generator, one stream of random generators can generate any kind of continuous distribution. Except like you have to worry about these cases, but let's not worry about that. So here's an example. So if I have the CDF, which is given by this, we'll see this is only for x figuring. This is going to be the CDF of the exponential distribution. We'll see shortly. If I want to create that, I will invert it. Inversion would give me this. So that's like the if inverse. So if inverse of u, you set it equal to u, and then you solve for x. That would give you f inverse of u. And so the random variable that is constructed as 1 over lambda, this is log, a natural log 1 minus u, where u is uniform. This is going to have a exponential distribution. Okay, so this is an example of a transformation of random variables. Um, so when you construct a random variable, which is a nonlinear function of another random variable, what happens to its distribution? This is an instance where you can easily figure out. Okay, so if the original one is uniform, and then the transformation is really a CDF, then the distribution of the new random variable has CDF exactly equal to, so sorry, the inverse of the CDF, then the distribution of x will be having the CDF exactly prescribed by what you put as the inverse there. There are the other ways of finding the distribution. So for example, there's a general rule to calculate the PDF of x from, for example, if you write it as a general function, so if x is like g of u, and u is differentiable, I can calculate the PDF um, of x from the PDF of u, and in this case, it will give you the same answer. So that's kind of a, we may see this later, okay, how to do it in general. But this is one example. Any questions about this? This is kind of important. Okay, let me move on. So this exponential random variable, let's define it. The idea is an exponential random variable is like the continuous version of the geometric. So if you remember, the geometric distribution had a memoryless property. And the exponential distribution has the same property in the continuous case. So the memoryless property is something like that. So if you have a random variable, you say it has the memoryless property if the probability that x is bigger than s plus t, given that you know that x is bigger than s, uh, is the same as the probability x is bigger than t. So x, you can think of it as the lifetime. So meaning is like the life of something. and you know that that something has been alive for time up to s, what is the chance that it will be alive t more units of time? And the probability of that is the same as just that thing living for t units of time. Okay. The fact that it has lived up to this point, this is, for example, people are not memoryless. Okay, so if you've lived 20 years, the chance that you live 20 more years is not the same as if you have lived 80 years. So the probability that you live 20 more years, uh, if you have already lived 20 years, given that you have lived 20 years. Okay, so given that you have lived already 20 years, you're bigger than 20 years old, the probability you live 20 more years, um, for this is not going to be the same as the probability that x is bigger than 20. Okay, it's easier to see if you look at it like 80 at 80. Okay, so if you've lived 80 years, you know that someone has lived 80 years, normal human being. The probability that they live 20 more years is not the same as the probability that live 20 years. Okay, there's memory, so you like the body does not forget that you've already lived 80 years. But let's say for like an electronic device, maybe this is true. So if your laptop has lived for 20 years, the chance that it lives for like 80 years at least. So it seems like some like maybe electronic like semiconductors and stuff like that. If I recall correctly, they may have this property. The failure, given that they already have lived to that point, does not depend on how long they have lived. But in any case, this is the meaning of the memory's property. In some cases, it makes sense. In some cases, it doesn't make sense. But a random variable that has this property, in the continuous case, it has to have a certain distribution. So to see it, um, I can write this probability as the probability of x bigger than s plus t. S and t are both positive. So s plus t, this is again lifetime again. It's lifetime. They're non-negative quantities. Okay, so this is like not true for humans. I mean, so far, not true for humans that we know of. Okay, so this and x is bigger than s. This is like the intersection. So if you remember the definition, this event intersect this event. Okay, divided by the probability that x is bigger than s. You want it to be the same as this by definition. So this quantity or this event is really x bigger than t plus s because uh, x bigger than t, like basically x bigger than s is included in x bigger than t plus s. If something has lived for t plus s units of time, it already has lived s units of time. Okay, if you have lived for 40 years, you've already lived 20 years. So this is a subset. So when I take the intersection, this is really the intersection. So the intersection would be, uh, sorry, the other way around. This is the other way around. So if you live 80 years, you have lived 20 years. But if you have lived 20 years, doesn't mean that you have lived. So the implication is this way, okay? So if you live this much, then you have to have lived at least S. And so this is a subset of that. And so the intersection would be the smaller set. Okay, so the intersection of these two events. So if this is A, this is B. B is a subset, so we have the probability. So A intersect B would be equal to B. Okay, that's the B. Okay, so what I get is from this is the memoryless property is equivalent to this. Um, and if I define like g of t to be the probability that x is bigger than t, then this is g of t, this is g of s, and this is g of t plus s. So what this is say is gt plus s is, if I multiply both sides, g of s times g of t. So this function, this is the complement of the CDF, has to satisfy this functional form um, here. Um, and the only function that satisfies this, and it decreasing has to be decreasing because this probability, the probability that is bigger than like the probability that x is bigger than t has to be decreasing as t grows. Okay, so it has to be exponential and it has to be decreasing, so it has to be after like, and then we have the condition that g of 0 is 1. The probability that x is bigger than 0 is 1 because we're going to assume that assuming that x is not negative. It's like a lifetime, the life of something like or the like the age basically, age of something. So g of 0 is 1. It's like g is decreasing, and it satisfies that this thing. So the only function would be something like exponential of negative something. That's kind of a mathematical result. And so this tells me what the tail probability, this is basically the tail probability. The tail probability of an exponential is e to the negative lambda t for some lambda. Uh, and the lambda is really as the meaning of a rate. It's the rate of kind of uh, decay of the probability. If this is large, then the tail drops fast. And if you have this, this is 1 minus the CDF, okay, because the CDF is the probability that x is less than or equal to t. Um, and so if I have this, then the CDF has to be 1 minus e to the negative lambda t for t bigger than or equal to 0. If you differentiate, you get the PDF f of t. The derivative of this, you get lambda e to the negative lambda t, t bigger than or equal to 0. So this is the PDF of an exponential random variable. Okay, so the exponential random variable is a random variable that has the memories property, and it's derived from the memories property and the fact that it's the tail probability is non-decreasing and is like 1 at 0. So that's the tail probability. This is the PDF. This is the CDF. And then you can use the tail formula. So because it's a non-negative random variable, the expectation of x can be written as the tail formula. This wouldn't improve, but it would be something like that. Whether you put an equality here or not doesn't matter because the probability that x is bigger than t is the same as the probability that x is bigger than or equal to t, since the probability that x takes value t is 0 for a continuous variable, remember. So it doesn't matter if you write it as bigger than t or bigger than or equal to t. For a discrete variable, it matters, but for a continuous variable, whether you put an equality here, it doesn't matter. So this would give me integral from 0 to infinity. I'm going to integrate the tail probability, you get something like that. This would be negative 1 over lambda e to the negative lambda t from 0 to infinity. And basically you get 1 lambda times 0 minus 1. So you get 1 over lambda. Okay. So the expectation is 1 over lambda. So it's really a rate. You can see it's like the rate of failure. So the larger this is, the smaller the expected lifetime is. So this is the rate of, let's say, decay or failure. If it's very large, then the whatever the object is decaying very fast, and so the expected lifetime is small. If it's very small, then it decays very slowly, so the expectation is large. The variance you can compute similarly, and it turns out to be 1 over lambda squared. Okay. So this is the equivalent of geometric random variable. Yeah, so the rough thing to remember is like things are as good as new. So given Sorolla to any age, the remaining lifetime has the same distribution as a fresh one. This does not hold for many things, but if it holds, then it is it has an like a it should have the exponential distribution. Questions about this? Comments? Okay, so let's see if we can finish this. So I think the only other thing that I wanted to, so we discussed uniform distribution, the exponential distribution. The really important one is the normal distribution, which I'm assuming you guys have seen. Um, and so this one occurs in a limit distribution as a limiting distribution of the uh, central limit here. So we'll see that. Um, it's hard to justify otherwise, but most people potentially have seen it. So the standard normal distribution written like this. So if you have a random variable that has a standard normal distribution graded as normal 0, 1, it has two parameters, mean and the variance. Um, and such a random variable has like defined to have a PDF like this. So the PDF is e to the negative z squared. So it drops. So comparing with this, the PDF of an exponential drops like e to the negative x if the rate is 1. And it's really 0 on the negative side and just drops like this, e to the negative lambda x, or like with unit rate, it would be e to the negative x. Um, the Gaussian would be double-sided, and it decays like e to the negative x squared. And we just normalize it. The normalization doesn't matter, but it just drops faster. So the tail goes down like e to the negative x squared rather than e to the x. And because x squared is positive, it can go both sides. And so the tails are faster, decaying faster, because I raise something to the power x, like x large, this is going to get larger than x, and the tail could go down much faster. Um, and the only thing that we need then is to normalize it. And it turns out that this is the normalization. So this allows me to integrate this to 1. Okay, so it has exponential to the negative a quadratic as a tail. And then the general case will have two parameters, mean and the variance. So this has mean 0 and variance 1. The general case you can construct from this, if you have a random variable that has normal with mean 0 and 1, if you construct a new random variable which is like mu plus sigma z, then this will have a normal distribution with mean mu and variance sigma squared by definition, and the PDF turns out to be this. Okay, it's shifted by mu, and then you get the scale here. Um, this one you can prove. This is, let's say, definition that you can take as the starting point. And then you can define a more general normal distribution like this. Um, the fact that if you define it like this, the PDF would be like that. This is an instance of doing the transformation random variable. You do, um, we didn't discuss it, but this is like a g of z. And if I know the PDF of z, and I know the functional form of g, in general, I should be able to calculate the PDF of x. I'll maybe discuss this briefly at some point. But this allows you to define, or like drive this. We'll drive it later, maybe. But that's the form of the PDF of a general normal. You can see if you believe, so this is going to be 0 mean because let's say if z is normal 0, 1. You can easily compute the mean, which is going to be z phi of z dz, negative infinity to infinity, because this is an odd function. It doesn't change if I flip the sign, but this flips this, like the sign of this flips. So the integral of z phi z dz from negative infinity to 0, if I break it like this, these to be negative of each other. And so they cancel each other out. So you can think of that later. And then for the variance, I need to be able to calculate this integral, and this is like um, you can do it in different ways, but one way might be using the integration by parts. So I'll let you try to figure it out. Okay, so we need to calculate this. This would give me expectation of z squared. Um, which will be equal to the variance because the mean is 0. So the variance in this case would be expectation of z squared minus the expectation of z squared. And this is 0. So the second moment is really uh, the thing. And then once you have this, the expectation of this follows from linearity. So mu comes out plus sigma expectation of z, and this is 0, so you get this mu. The variance of x follows as well because you get the variance of mu plus sigma z. You know that you can drop mu, so you get sigma squared variance of z. That's a fine transformation formula, and this is 1. So the fact that this general form has mean and variance sigma squared, mean mu and variance sigma squared follows from properties of linearity of expectation and the affine transformation property of variance. So the CDF does not have a closed form, but potentially you have seen it before. Yeah, so it's like everywhere because of the central limit theorem that we'll see. If you add a bunch of IID random variables, the the distribution of the result approaches a normal distribution. The CDF does not have a form, but usually you write it as a phi. So the CDF of this is written as phi of capital phi of let's say t if you want. It's like negative infinity to t. And numerically you can calculate it. And then the CDF of this is easy to see. The CDF of this one would be um, phi of um, x would be x minus mu divided by sigma. Um, this is again easy to see. So, and then it's tabulated, so the probability that like standard normal is less than 1, this is like 0.68, and then bigger than, like less than 2 would be 0.95, less than 3 would be 0.997. I guess you most likely know these things. Okay. I think we're done here. So I wanted to very quickly go through these. I'm assuming that you know this, but we'll come back to the normal distribution later. But that's kind of covers the remaining material from here. Any questions, comments? Okay, let me stop recording here.